Today it's going to be chapter 24, algorithm design method. We are going to learn about these things. What is the purpose of a decision table? Construct a decision table with a maximum of three conditions and simplify it by removing redundancies. Redundancies mean like duplications, extra. Construct a JSP structure diagram showing repetition. JSP, Jackson structure, structured programming. Construct a JSP structure diagram showing selection. Write equivalent pseudocode from JSP structure charts. Construct a JSP structure diagram to describe a data structure. Construct a JSP data structure diagram using sequence, selection, iteration. Construct a JSP diagram for a program design. Use state transition diagrams to document an algorithm and show the behavior of an object. So it's going to be an interesting chapter. Decision tables. A decision table is a precise way of modeling logic. Each possible combination of conditions is considered in turn and what action is required. I'm sure this will bring to your memory about truth tables, where all the possible combinations of input to a logic gate and the outputs thereon. Decision table, a precise way of modeling logic. A decision table has the format shown in figure 24.01, that is these conditions, then condition alternatives, and action entries. Let's see what they are. This is an example. Students in a particular college take an end of year test. Any student with 90 marks or more gets a distinction. Students with fewer than 20 marks fail. All other students get a pass. We set up a decision table by allowing one row for each condition, and one row for each possible action. These are conditions and these are actions. We need one column for every possible combination of conditions. One column for all the possible. Two conditions require four columns. Right? Two conditions, four columns. Three conditions require 8 columns. So does it bring anything? Does it take you back to the logic gates, the truth tables? 2 to the power 2. If two conditions, 4 columns, three conditions, 8 columns. Right? 2 to the power n. If it is 3 conditions, so here the conditions are n. Look at this decision table example. In the conditions row, we have one that is greater or equal to 90 marks. What is that? Here. It's coming from here. 90 marks or more. That's one condition. 90 or more. You put Y. Then what is the other condition? Less than. Fewer than 20 marks is less than 20 marks. So this. So there are 4 conditions here. One is both are true. You take in the logic gate, the truth tables, we took 1 and 0, the binary numbers. Here, Y and N also can be the same. So you can take the next one. Which is greater than 90 marks. Greater or equal to 90 marks is yes. And less than 20 marks? No. Can't be no. If this is greater than 90, this has to be no. So then you get a distinction. And here you will again, if you look at this, what is greater than 90 cannot be less than 20. So this is why you put a dash here, that nothing can be true. There are some blanks here, but this is different. It cannot be. It's impossible. Here, greater than 90, distinction. This one, this column shows less than 20. So it can't be more than 90. No, it's no there. And the result is fail. And this is not more than 90 and not less than 20, which means between 20 or between 20 and 90. Between 20 and 90, it's a pass. It's simple. It's simple. Again, I'm telling you, though this is simple, if you are given a question, if you have not done this, you will find it difficult. So you have to do, you have to do. I repeat, just reading this or listening to me will not help. Note that y means true and n means false. Like 1 and 0 in the Boolean logic we used for truth tables. X means this action needs to be performed. So X is the action that is to be performed in this truth table, in this the decision table. So a dash is added where the condition alternatives are irrelevant or impossible. So this is either irrelevant or impossible. A student cannot have fewer than 20 marks and at the same time at least 90 marks. The real power of decision tables becomes apparent when the conditions and resulting actions are more complex. Inspection of the action entries sometimes shows redundancies and the decision table can be simplified. This means the program code to be written will also be simplified. So that reminds us these decision tables are drawn in order to do programming code, write programming code looking at it. Here is a worked example, creating a decision table. Consider an online order company that charges $5 for delivery of packages. If the order value is over 50, the package is small and the customer has a promotion code, the delivery is free. So there's a combination of conditions. Another one here, if the order value is over 50 and the package is small, the delivery charge is $1. Right? And there's a third one. If the order value is over 50 and the customer has a promotion code, the delivery charge is $1. Now here, you have to simplify this like this. Now the first one is all three are present. What? Over 50, yes. Package is small, yes. Now supposing those are now that is how you can build up the table. Customer has a promotion code, yes. In the second one, order value over 50 years, package is small, years, and what else? It is not given there. The promotion code, no, right? Yet then it is $1. The third one is more than 50 years, promotion code years, but small package, no. But yet it's $1. Then but when do you get $5? All other instances, like for example, less than $50, the package is $50. Then if the package is big, no code, no promotion code. So things like that will take place. So let's see. We complete the conditions in a decision table for the order form in the systematic manner shown. The table shows the delivery charge conditions. What are the delivery charge conditions? Here, the first one I told you Y. Order value 050, small package yes, promotion code Y. Second condition is order value more than 50 years, small package Y, but no promotion code. Then this way, more than 50, big package, promotion code yes. Like that goes. Can you see a pattern here? And isn't it familiar? If you take like this 0 for n and y for 1 for y, then here 0 0 1 0 1 0 0 1 1. Also look at this way, then you will know what it is. 3 conditions, 1 2 3 4 5 6 7 8, 8 columns here, 8 columns. Then divide by 2. I'm just describing something, see whether you see the relevance. Remember the rules of another section. Divide by 2 for the next column. This is row, but what I am referring to in that it was a column. And divide 4 by 2. First of all, this is 8, divide by 2 and 4 y's and 4 n's. That means 4 zeros and 4 ones. Then divide by 2 and put 2 zeros, 2 ones, 2 zeros, 2 ones. Then that divide by 2, and then 0, 1, 0, 1, 0, 1. This is the way we did the truth table for the inputs. The 3 input logic gate truth table is this. There is no output, these are only the inputs, right? Next, we look at each combination of conditions in turn and decide which action needs to be taken and mark those with X. So here it is. All 3 conditions true, free delivery. Then 2 conditions, the order being more than 50 and small package, yes, $1. 2 conditions, $1. Here, order more than 50, not a small package, but promotion code. Again, $1 charge. $1. In all the other cases, it's $5. You understand? All these are less than $50. Then these 2 are small packages. This and this promotion code. But when you take the combination, you won't get a discount or free delivery. It's the normal charge, $5. To find redundancies, we look at each action and then check whether the conditions are required. Free delivery only applies if all 3 conditions are true. There are no redundancies here. There's nothing, no problem. Straightforward. No extras also, only one case. The $1 charge applies if condition 1 is true and either condition 2 or condition 3 is true. There are no redundancies here either. So here also straightforward. The $5 charge applies in all cases where condition 1 is false. See, there's a common factor here. If it is false, then no need of the other things. This is straight away false or $5. We can therefore, the redundant conditions are shown by this shaded cells. So these are the redundant ones. Because it's not definitely when this is, of course, we found that when these things happen, it becomes $5. But we found that it's a common one. If this is no, that is enough. Because here you don't get that. No is not there. No is only here, and all 4 cases it's X. The redundant conditions are shown by the shaded cell. We can therefore simplify the table. Put a dash in the cells where the condition can be true or false. The action will be the same. The dash is sometimes referred to as the don't care symbol. Okay, so this is the simplified one. No change here. The first 4 columns, no change. The last 4 columns can be given only in this. Just one column is enough. The moment this is no, it is X. It is in the sense $5. $5 delivery charge. Decision tables can also be used to define outputs dependent on inputs. So can be a basis for testing a program. So talking about program testing, we use this is just a revision, right? We use test data, and before running the program, we have to do the calculations and keep the answers ready. Then we run the program and see whether we are getting the calculated answers. So for that also, the inputs, various inputs we can have, the test data, and the outputs marked beforehand, predetermined. JSP, Jackson Structured Programming. When designing a program using Jackson Structured Programming, we set up a structure based on the structure of the data the intended program is to handle. What is the structure of the data to be handled by the intended program? We are going to write a program. A structure can consist of elementary components. That means they have no paths, and composite components, which means sequence, selection, or iteration, like control structures. So a structure can consist of elementary components and composite components. A sequence has 2 or more components. Selection consists of 2 or more paths, only one which is selected. Iteration consists of one part that appears 0 or more times. Can you link this to what you already know? A sequence has 2 or more components. An example, A equals 10, A equals A plus 1, that is two statements, or more in sequence, in order, that is a sequence. Then a selection consists of 2 or more paths, only one of which is selected. That refers to or relates to if then else selection condition, a decision. Then iteration, the meaning of which is repetition. Looping consists of one part that repeats 0 or more times. Why 0? Because some loops don't take place. At the beginning itself, the condition is false or true depending on the loop you are using. Then it ends there without repeating anything. The first time is done, but no repeating. Or more times, repeating more times, many times. So here is a designing a program using JSP. Consider a company's order form template. See, parts order form, that is the beginning, the top one. The customer name, customer address, then going down to smaller ones, parts like each part is described, the price is calculated, the total price, various things. Right? The first stage of designing a program to process the data in this order form is to draw a data structure diagram of the data. Using the top-down approach, at the top level, the order form consists of these components: the header, the order, body, the totals, and the payment method. Okay. Is the header. The header, order body, the totals, right? Totals here, and payment methods here. Check, bank. The header is a sequence composite component containing customer name and address. The body is an iteration composite component containing repeated products and their quantity. See, this is just a sequence, no? Type the parts, order form, then customer name. No repetition, no decisions, just in sequence it is done. This and the headers, all this is done in sequence. Then comes the body is an iteration composite component containing repeated products and their quantity. So these are iteration because this you do the product ID, description, quantity, unit price, and the price is calculated. Quantity into unit price is the price. Then you repeat for the next product ID, then the next product ID, like that. It's a iteration. The payment method is a selection composite component containing either check or bank card. So here is a selection, either check or bank card. So the operator will input one of them and the output should be different. On the data structure diagram, repetition is shown by an asterisk in the corner of components that are repeated. Selection is shown by a circle in the corner of components where only one is chosen. See, this is just a selection here. This is a repetition where the asterisk is there. And here, sorry, this is a repetition. Yeah, this is a selection. Whether the check or bank card is a selection. And here, product ID into quantity, like a repetition. You do this for all the items. Order body, it's a iteration. It's difficult to remember this sign. Why is that? Because if you try to remember this as a loop here, the circle, this is a small circle, is like a loop, but it is not. It's a selection here. Here is a loop, asterisk. So how are you going to remember that? Think like this. If you have check and bank, you have to select like a checkbox. Tick box or checkbox. You see, like a circle, no? In the circle, you tick for selection. If you think like that, then it's okay. This is selection, not a loop. Because naturally, your natural inclination is when you see this circle, it's like a loop. To connect it, link it, and remember like that, then it's wrong. Like this selection box, this selection, you just tick which one it is. And here, iteration. so many, the star has so many going out like that, repetition. But I would suggest that you all make your own, make up your own way of remembering it. Find a way of remembering it. Don't make a mistake. Write pseudocode from the Jackson program structure diagram in figure 24.04. So you can write pseudocode using this diagram. That's a task for you to do. In more complicated systems, the output data can be subjected to the same analysis, possibly leading to conflicts to be resolved. So there can be the complicated system, output data can be subjected to same analysis, possibly leading to conflicts to be resolved. So there can be, the complicated ones can have conflicts, but they have to be resolved. Then we come to another new section, state transition diagrams. A computer system can be seen as a finite state machine, FSM. There are innumerable now it's number of states. The states cannot be counted, how many states. And FSM has a, I mean, actually, no, it's the real meaning is limited. Like there can be so many, but finite. The computer system can be seen as a finite state machine. So you can think of a limited, like it's not infinite, not infinite. An FSM has a start state. An input to the FSM produces a transformation from one state to another state. Okay. In simple words, think of an input which will change output. The transformation about the states of an FSM can be presented in a state transition table. State transition table. Finite state machine FSM, a machine that consists of a fixed set of possible states with a set of inputs that change the state and a set of possible outputs. State transition table, a table that gives information about the states of an FSM. This table shows an example FSM represented as a state transition table. Finite state machine represented as a state transition table. If the FSM is in state S1, an input of a causes input of A causes no change of state. See, this is S1. The input A doesn't change the state. It's still S1. If the FSM is in state 1, FSM is in state 1 and input of B transformed S1 into S2. See, the current state is S1 of the FSM, finite state machine, and the input of B changes the state into S2, state 2. If the FSM is in state 2 and input of B causes no change of state, okay? When it is in S2, the input of B doesn't change, it remains at S2. If the FSM is in state 2 and input of A transforms S2 to S1. So in this case, A does a change here when it is in S2. When it is S1, B does a change. Okay, a state transition diagram can be used to describe the behavior of an FSM. Figure 24.05 This one shows that state as start state. Figure 24.05 shows the start state as S1, denoted by this arrow here. Start S1, starting, and the state is state S1. If the FSM has a final state, also known as the halting state, this is shown by a double circle state S1 in the example. Double circle S1. That is when, if the FSM has a final state, so FSM has a final state also, then S1, shown by a double circle state S1 in the example. If an input causes an output, this is shown by a vertical bar, as in figure 24.06. If an input causes an output, state transition diagram with inputs. See the vertical bar is this here. A. Now it was A here, the input. If an input causes an output, this is shown by a vertical bar. For example, if the current state is S1, an input of B produces output C and transforms the FSM to state S2. So input of B produces output C and transforms the FSM, this one, from S1 to S2. All right, so input on the left side, output on the right side. There's a vertical bar in between. Here's a worked example, creating a state transition diagram for an intruder detection system. A program is required that simulates the behavior of an intruder detection system. Description of the system. The system has a battery power supply. The system is activated when the start button is pressed. Pressing the start button when the system is active has no effect. So when the system is active, already in operation, if you press the start button, no effect. To deactivate the system, the operator must enter a PIN. Why? Otherwise, the burglar who came in can deactivate just by pressing a button. So only the house owner can deactivate by entering the PIN. PIN is personal identification number, like in ATM cards. The system goes into alert mode when a sensor is activated. So when the burglar comes, when the sensor is activated, sensor signal, the system will stay in alert mode for 2 minutes. Right? It won't go immediately back, otherwise it will start again. So 2 minutes is a reasonable time. It depends. The 2 minutes is decided by the researchers of that unit after testing. If the system has not been deactivated within 2 minutes, an alarm bell will ring. So what does that mean? If it goes by mistake, accidentally, it starts. It's activated accidentally by the owner himself or an animal or something. Then the system will stay in alert mode for 2 minutes if the system has not been deactivated. So if it's by the owner, house owner, he has 2 minutes. Within the 2 minutes, he will deactivate it. If it's not being deactivated within 2 minutes, an alarm bell will ring. So that means maybe the owner is sleeping and it has gone for 2 minutes. So it's a real alarm. Burglar has come or some kind of person has entered or whatever detected. We can complete a state transition table using the information from the system description. So at the beginning, the current state, system inactive. Event is press start button. The next state is system becomes active. Again, if the current state is say active, then if you press the enter the pin, if you enter the pin, then the system becomes inactive. Then third state, system active. When the system is active, activate sensor. Then it goes to alert mode, the change. When the system is active, press start button. System active. What is the change? There is no change because the state is system active, and system active means there is no change. At the beginning we discussed in the story, it was there. When it is active, if you press the start button, nothing happens. Then when in the alert mode, if you enter pin, system becomes inactive. So that's a way of deactivating the alarm if it went off by error, by accident. Alert mode, when you are in the alert mode, 2 minutes pass, then the alarm bell rings. While in the alert mode, press start button, alert mode, that means no change. There's no change. Alarm bell ringing, enter pin, system inactive. So when the alarm bell is ringing, when the owner comes near the controls, then that means that is enough. So the moment the owner, house owner enters the pin, the system becomes inactive. Then while the alarm bell is ringing, press start button, alarm bell rings. There is no change. Same state continuing. Because there is no point in pressing start button when the alarm bell is going. The start state is system inactive. We can draw a state transition diagram from the information in table 24.06. See whether you can figure this out. Start button, press button, system becomes active. Press button, same thing, no change. At that time, enter pin at this stage. When the system is active, system becomes inactive. All those are there. Let's see whether that particular one is there. System active, enter pin, system becomes inactive. Sensor activated, then it goes to alert mode. Press the button, nothing happens. Then enter pin, system inactive. 2 minutes pass, in the alert mode, 2 minutes pass, then alarm bell rings. Press the button, nothing happens. Yeah, nothing happens. Alarm bell will keep on ringing. Then enter pin only will make it inactive. So that whole table is represented in this diagram. State transition diagram for intruder alarm system. Worked example. Creating a state transition diagram for a tools complement FSM. A finite state machine FSM has been designed that will take as input a positive binary integer, 1 bit at a time, starting with the least significant bit. The FSM converts the binary integer into the two's complement negative equivalent. Two's complement negative equivalent. The method to be used is output the bits input up to and including the first one. Output the bits input up to and including the first one. Then step 2, output the other bits following this scheme. So zeros and all that, if there are, first you have to input zeros and stop at the first one. The first bit which is 1, up to that you output and stop there. Then output the other bits following this scheme. For each one, output a 0. For each 0, output a 1. So from that point onwards, just invert it. This information is represented in the state transition table shown in table 2407. Current state is S1, input bit 0, next state is S1, no change. Output bit is also 0. Then the next one is S1, the input bit is 1. Next state is S2 because it changes. We are only up to that point we do. And the output bit is 1. After that, S2, when we input, it's the same state. State doesn't change. But what happens is, when you input 0, it becomes 1. The ones, it will be 0. That is how you calculate 2's complement, the shortcut, if you remember. Calculate in the 2's complement, the shortcut method. Otherwise, the long cut is you hash it with XOR. You XOR, like that is 1, 1, 1, 1, 1, 1, all ones. If you XOR it, then it becomes the inversion and add 1. That is the 1's complement before adding 1. What you XOR with, you XOR it with 1, 1, 1, that becomes the 1's complement. Then if you add 1 to that, then that becomes 2's complement. So this is a shortcut method. You write up to, from the right side, from the least significant bit, take up to the first one. The first 1 bit. And you write like that. Even the 1, you write like that. See? The 1, though it changes, though the state changes to S2 for the next step, but you write 1. So the zeros and the first 1 is written. After that, all inverted. I'm sure it's clear now. This method can be represented as the state transition diagram like this. State transition diagram for a 2's complement FSM. Start S1, 0, nothing changes. You go on outputting the 0 also. Then the moment you put 1, the output is 1 here. It changes to S2. Afterwards, if you put 0, it becomes 1. Go on like that, and 1 becomes 0. That is how it can be represented. Task 24.02. Write a program that simulates the intruder alarm system in worked example 24.03. Use Python for this program. Question 24.01. What is the output from the FSM represented by the state transition diagram in figure 24.08 when the input is 0, 1, 0, 1. So 24.08, the figure. Figure 25.07. Then here is a figure 24.08. From that, if it is 0, 1, 0, 1, what happens? That's the question. When the input is 0, 1, 0, 1. You have to consider that you are inputting from the least significant bit, though it is written like this. Right? Extension question 24.01. Does the FSM in figure 24.08 work for converting a negative binary number into its positive equivalent? That's a very good question. You just have to answer that. But you'll have to work it out and see. And the summary of the chapter is a decision table shows all possible combinations of conditions and the resulting actions. A decision table may show redundancies that result in a simplified decision table. Jackson Structured Programming (JSP) is modeled on the structure of the data. JSP structures consist of elementary and composite components. Composite components represent sequence, selection, or iteration. So elementary are the simple statements, just single statement, but composite components, the sequence, selection, or iteration. A finite state machine FSM has a start state. A state transition table shows each state of a FSM and the events that produce a transformation from one state to another state. A state transition diagram is another way of representing states and transformations of, of an FSM. And here are the exam style questions. Once you do these, you are able to do some past paper questions also. And next time, chapter 25, which is recursion. 24 done. Next time is tomorrow, chapter 25. Okay, so that is the end of today's lesson.